Hi guys, welcome to Learn Electronics Repair. I have a PCB here. Little story to this one. So one of the channel subscribers, a guy named Roger, this is his real name, came over to Gran Canaria on holidays, never been here before, and in actual fact it was my recommendations to say come and visit the place, which is why he's here. And the first thing I will say, he's having a great time here. And the second thing I will say is that he brought this PCB with him. So this is from a MIG welder. I don't know anything really about these welders because I don't weld things, but apparently this is the type where it has a wire that feeds into like the nozzle or gun, if you like, the welding gun, if that's the correct term. It probably isn't. And it passes a high voltage, so like an arc, I guess, like an arc welder, I might call this. As I say, I'm not a welder, I solder, okay? So he says that this goes into the unit. There are two potentiometers. One controls the rate at which the welding wire feeds in, and the other one controls the strength or the pulse. I think it's like a pulse width or a duration, should I say, the duration of the welding, okay, which I guess is done like in bursts, but again, I'm not a welder. So you can all have a laugh at my lack of knowledge of that and see whether I can actually make a better job of trying to repair this. He says that when he first received this, it was completely dead, and that this capacitor, this large capacitor, was all corroded on the top. So he's changed this capacitor, but he freely admits, because he's not so experienced in soldering, that there are tracks on both sides of the board going to the capacitor, and that the tracks on this side were damaged when he took the capacitor out. So what he's done is, and this is pretty good actually, we can see we have the pins, or legs if you like, of the capacitor here, and these wires, one strapped from here to here and one from here to here, are effectively to repair the tracks which are damaged on the other side of the board. So he changed this capacitor, powered it up, and he found then that the red LED, this one, illuminates, whereas it didn't previously. So it looks like, Roger, you've managed to fix one fault on this, but it's still effectively dead. Although the light comes on, it doesn't do anything. So the question is, or rather questions, one, can I fix this or try to fix this? And two, how to go about it, okay? So the first thing I'm going to do is a visual inspection of the board. I'm just really, at the moment, just checking for burnt or broken components. I assume Roger already did this, so if you've already done this, mate, I'm just doing this again on camera, okay? You didn't mention any burnt components, but what actually you did mention was that this resistor here is getting quite warm, okay? And that you've changed this resistor, but it still gets quite warm. So apart from looking for burnt or damaged components, is that one a little bit defective just there? Let's have a look. I don't think so. So that is a 6.8 and 20 6.8k resistor. So we can just check that to see how it looks in circuit. If it reads 6.8 or less, it's probably okay. If it reads more than 6.8, considerably more, there's some sort of problem here. And it reads 6.77. In fact, it reads very close to its rated value. Quite possibly because one end is connected to a capacitor. I don't know if it goes anywhere else. So in other words, there's nothing much to affect the reading. Okay, we have a few more components, all look good. We have a chip here. So this is a LM324. So this is a quad op amp. There's no connections around here. I'm not sure if all three op amps are being used. They probably are. So this would be in, out. I think it's non-inverting, inverting out, non-inverting, inverting out. So they probably are. These are probably used on the other side. Yeah, maybe. I'd have to examine it a bit more, but That's what we have there, okay. Quad op amp, but certainly some of them are being used. There's a connector down here. I'll tell you what Roger told me about that in a moment. Variable resistor, another chip. This is SG3525A. I know this chip. This is a pulse width modulator controller. Yeah, for driving MOSFETs. Usually this is in things like ATX power supplies and similar. This is to drive a transformer at a high frequency pulse width modulation. Okay. Another quite hefty resistor there. It looks okay. A couple of capacitors. This is a big transistor, TIP147. That's some sort of bipolar transistor. There's another one here, P30N06. This is a MOSFET of some sort, power MOSFET. Couple of low value, high wattage resistors, bridge rectifier. There's a relay here and another connector. Okay. Oh, with a big inductor coil. So the information I have. These are the wires that come in on this large connector here, okay? And then the small connector goes there. Now, Roger's given me a list of the colours of the wires, okay? And he's marked some, so he's saying brown and black is power, 27 volts AC. So that's coming in across here to here, either end, okay? Certainly goes to that bridge rectifier, I would say. And DC 36.3, so that's the DC that comes out of this bridge rectifier. That'll be connected to this capacitor, I'm certain, to be quite honest. Okay. Then the purple and orange wires, orange purple, this is the wire feed motor. It doesn't say if it's a DC motor or an AC motor or what it is, but that's where the motor attaches that feeds the wire. And the pink and white is the wire feed trigger. So this is some sort of switch. I'm guessing you probably hit a trigger switch to feed some wire. Okay. He's saying the pink has 3.6 volt on. So just guessing white is probably the ground end of this power supply. In fact, it says DC minus. He's written on there. But he doesn't really mention, well, he just mentions the trigger, okay. Pink, so he's saying pink has 3.6 volts on it. This may be a case that when you pull the trigger, it grounds that, so this is effectively a signal which then signals something on here to start the motor, okay. This is all supposition, guys, but of course, as I've said many times before, when you're faced with an unknown PCB like this, it's probably all you do have. The grey comes from an isolator. He said this is what he called a galvanic isolator. I asked him a bit further and it appears that it's like some sort of heavy duty relay, I think he's trying to tell me that is. I googled galvanic isolator and he didn't give me the exact, but that's what I have. Roger, you're probably watching this, you might like to comment on that. So there's 27 volts AC, which is the same as that, between the grey and black. Okay, so the brown and black have 27 volts AC, and the grey and black also has 27 volts AC. Okay, so that's what that's telling me. Now, how would I start on this? Well, because Roger tells me he gets DC coming out of here, I think we can pretty much assume that the AC is connected to this and this is connected to that. Let's have a look. So this is the minus and this is the plus. That's that end, which is the positive end of the capacitor, and that's this. I'm assuming he's used the red and black. This is the negative end, so yeah, that's where the bridge rectifier goes to. And what I suggest doing, because I don't have a suitable AC source here, is to put DC into here. So I'm going to connect DC across the bridge rectifier. Now, Roger also tried this, so I won't say I thought of that straight away, although this is what I would have done. But he said he only applied about 9 volts here. I'm going to put the full, well, my power supply goes to about 32, so I'm going to go basically to the voltage that would normally appear across there. The capacitor's 35, so it's pushing it to the limit. I'll put 30 volts on there. I mean, that's what he's telling me, so what do I think? You know what? I'm going to have a look at the maximum supply voltages for these chips and see what that is. I mean, they may not be supplied directly from there, but I'm certainly not going to put more than that, okay? So while we're on that same train of thought, let's have a quick look at the datasheet. So LM324 and the SG3525A. Okay, so LM324 quad op amp. I was wrong about the layout for this. I was working on the layout from a dual, basically. I was wrong, but I've looked it up. Possibly that some of these are not being used, as I was looking at the tracks on this board. I have a suspicion that this one isn't in use, okay, but it's using some of the other ones. Yep, that's sort of how it looks to me. So this has a maximum working voltage of 30 volts. I want to keep the supply below that, okay? The SG3525, we have a data sheet again. So this has up to 40 volts, okay? So I will take the DC at 36 volts as a bit of a pinch of salt, and I'm going to put a bit less than 30 volts into it. I might just go with 24 actually. Again, there's a lot of guesswork involved, but both these chips would work at that sort of voltage, so shouldn't really be a problem. And maybe they're not supplied directly from the main capacitor anyway. There may be something else that's dropping the voltage. Once again, once I put some power on the board, I can measure the supply voltage on both these chips and see whether it effectively makes sense. Yeah, see if it is directly supplied straight away from that large capacitor. What else do I see? Well, there was a very large transistor, TIP147, and there's another, the MOSFET there. There's a few little transistors, nothing notable. There's a few diodes. So as a first check, before I power this up, I'll probably just have a look at semiconductor junctions, just to see if I can see any problem. There's nothing on this side, so this is a quick poke around, but looking for faults. So this thing, yeah, 2SC3374, something like that. Transistor, certainly. Same, definitely a transistor. So there's the two small ones, the MOSFET and the big one. And there's no other transistors, but there are some diodes. And these are all things we can easily check, at least to see if there's any obvious problems. Okay, so diode mode. This 2SC is probably an NPN transistor. Sometimes these have the base in the middle. I don't know exactly, but we can kind of find out. So that reads like a junction. That reads like a junction, so it looks like NPN with the base in the middle. Do I read anything across here? Yeah, just a climbing up reading. That's probably NPN transistor and looks okay without taking it out of the circuit. Diodes, very easy to test the diodes. Reads okay. I won't bother with all these little resistors, but I will go with the diodes. Reads like a diode junction. Yeah. Same. Reads like a diode junction, so that looks okay. Variable resistor we can check very easily, but on these are resistance range, so let's do all the semiconductors first. Again, diode. Reads okay. MOSFET, so normally I'll probably end up taking this out of circuit, but I'll do it from underneath, it's going to be easier. And again, he's repaired some tracks here. He's either taken this out or to test or to change. I expect this to be pretty much open. Pretty much open. And if it's an N channel, you probably expect this parasitic diode from here to here. No. Or from here to here. Depends on the pinout. Oh. Well, that's either short or it's connected across something that's short. So that we need to look at. Okay. What else do we have? Just a quick poke around. I mean, that may affect some other readings, of course. That may be something to do with why this resistor's getting hot. Large diode here. Let's have a look. Reads short, but that could be conceivably across this inductor coil. So again, we need to take it out to test it. Or it could be a short on one of these two, okay? Here. Reads okay. Here. Reads okay. Here. Reads okay. Another diode down here. Reads okay. That could be a Schottky 1N58. Oh, probably a 5819. Very common Schottky diode. I'll take that as being a Schottky because of the reading. And the marking seems to suggest that as well. Another transistor. So if these are NPN, and I measured the previous one, base down in the middle, positive lead, should be junction. Yeah, and then a junction to that way, okay. And then like a climbing up reading across here probably. Just get into it, a bit awkward. Yeah, it reads basically open. Yeah, the same climbing up reading I got on the other one. Probably okay. Then we have another diode. Okay. And that's about it for semiconductors apart from this one. So I'm confident enough this will be the base. Reads like a... No, not like a diode junction. It's just continuing to climb up. Reads quite low. Let's come the other way. So reads like a diode junction. This is probably a PNP transistor. So base collector. And then why I'm seeing a lower reading here is a collector. Sorry, is a base to emitter resistor. And you would quite often expect that to be a fairly low value. Could be one of the ones around here somewhere. That reads different too. It's probably this one. Again, guys, this is just guessing. Yeah, not that either. Okay, so there's a short around here somewhere, this or this. I'll lift the end of the diode first. That's the easiest thing to do. And see where the short then disappears from the other one. So just to confirm. It doesn't actually read short now, it reads close. Did I turn this MOSFET on? Let me just look at this. So that reads like a low resistance. Here to here. Okay. This is the MOSFET. There. So gate is on this pin. This is the gate. So if I go gate, drain, gate source, it reads effectively open. And it now reads like a short. Let me put the black lead on here. So it's effectively switch these off and go again. Look, it's not short at all, yeah? It's not short at all. I'm turning this MOSFET on by putting the positive lead onto the gate. Now the fact I can do that suggests that this gate is floating. Yeah? And that in itself is a little bit strange. So once again, you see, I'll put the red onto here. which switches the MOSFET on. Yeah. Put the black onto here, which switches the MOSFET off. Does that also take the short from here as well? So this is a big diode. That's now reading like a Schottky diode. Okay. I don't think I have a short at all, but what I do have is that the gate of this one appears to be floating. And you wouldn't expect that to be floating in a circuit. Did you get that, guys, by the way? If not, ask me in the comments below if you didn't get what I'm thinking. So this goes from here to here, probably, which is the top one of these, which is a fairly low value resistor. The colour balance is really bad on this camera. Reds look like browns sometimes, but what do I have? Go to ohms range. 2K. Yeah, it's probably a 2.2. Red. It's just the colour balance looks weird on the camera. Oh, then that goes to a capacitor. If it is a, yeah, it is a capacitor. Yeah. That would mean to DC the gate of that is floating, so and then it goes to another capacitor and then to this lot. It's interesting, but it kind of explains why I see a floating gate on there, though. I'll give it that at least. It doesn't seem to go anywhere else. Oh, it does go elsewhere. My mistake. It goes down here. Okay, and there. So 1, 2, 3, fourth one down. Yeah, and the fifth one. So that also comes down to, that also comes to here. Oh, this is a high value resistor. Yeah, from there you can see it comes down to here. That's 100k. That's a high value resistor, actually. That may be something to do with why that gate floats. Then that goes to another capacitor, and then down towards this op amp. Bit of a strange circuit, that, guys. I may end up having to draw that out, but I'm going with the basis so far that there's nothing actually wrong with that circuit, unless you guys convince me otherwise. Okay. While we're on resistance range, let's look at these pots as well. So this effectively should read the resistance of the pot, which I think is a 10k, and that'll read to the wiper 3.9, 5 point something. And if I adjust it, the reading should change. Yeah, 390 ohms, 6.9. So we say that's fine. This one. Oh, these are like 0 ohm resistors, I think. Might be worth checking those. Let's have a look. So I doubt the, you know what, I say worth checking these, but I can't see these being faulty, because normally a 0 ohm resistor goes faulty because too much current went through it, and you can't have too much current going through this pot, not without burning it up. Yeah, it's fine. Right, so again, potentiometer end to end should read the resistance of the pot. 110k, it's probably a 100k, there's one. To the middle, 22k, and this side, onto it, 69k, again we'll just adjust it. Okay. So one reading will go up, probably this one, 77, and this one has probably gone to 0 now. I think I've turned this all the way over. Yeah. Yeah, 10 ohms. There's a couple of these little preset type pots here. You can see again, these are always worth checking because these things can fail. they're kind of a partially mechanical, so 10k. Oh, that means 37. Yeah, 37. I would say 100k. There to there can't be more than there to there. Yeah, it's 100k and 37. This one 60 something now, 70. You can adjust these things. He doesn't actually know what these adjust, but they adjust something. I'll just put it back in a minute, but the values change. That's the one thing I wanted to know. Yeah. So that looks okay. Last one. So I hope you think, guys, I'm not just poking around here aimlessly. I am actually having a look to see what we have. Just adjust it slightly. That's actually all adjusted all the way to one end, that one. Yeah, it's changed. It's changed, that's okay. Put it back to one end. Right. What else? Small value resistors. Large, low value resistors, yeah. Again, they look perfectly fine, but we'll just check. So, here, this is almost going to be short. Yeah, pretty much. I mean, this is a 0.56 ohm resistor. This one's a 0.15. This one goes across here, I think. Well, that reads 109. We're in the wrong place. Where's this thing connected? So you can see where it goes. Doesn't go across there. It's all. It ends up here. Yeah. Okay. They read okay. So this large transistor reads okay. If it has a base emitter resistor, it probably does have. So because this is a big transistor, you would assume the power is going to come into here. Unless it's like via something to here. Could be, we'll have a look. So either power is going to come in on here, the collector, I would think. And a load driven from the emitter, or the other way around, power via something out here to the collector, then the emitter to ground. Let's have a look. So this is base collector emitter. Okay, so base is here, the one with the thin track. This is your bridge, so let's have a look. So from this end of the bridge, this is the ground end. Reads some resistance to there. So that doesn't connect to either. How about the other end? This is a positive. Oh, the positive goes to the emitter. Well, that suggests then that this is a PNP transistor if the positive is going there. And then the collector is probably driving something. Let me show you what I mean. Here is the TIP145, and we can see this in fact is a Darlington transistor, and it is PNP. Okay, that kind of makes sense from what I was seeing on the board, the way it's connected. So we have a bridge rectifier. This is not mains, this is something like 27 volts AC. Okay, plus minus, like so. We have a large electrolytic capacitor. This is the one that Roger changed and damaged the tracks. And then we have this transistor, this TIP147, and that is connected emitter to the positive supply. This, I think he said, was about plus 30 6 volts, although I kind of am not sure, but that's what he says, so let's believe him for now. Collector, base. So the transistor is connected like that. Now, this tells me a couple things straight away. Firstly, this is either being used as a voltage regulator to give a lower voltage here and stabilised, or it's being used as a switch to switch something, okay? Maybe with pulse width modulation, one or the other. It looks probably a bit more sensible if I put the transistor that way round. And you can see that either this can give a regulated voltage if we put a fixed voltage on the base, or if we don't put a fixed voltage on the base, it could, for example, be switching something like a coil to ground, yeah? Something like that, a transformer. He says there's 2 transformers in this unit. My suspicion is that the first transformer steps up the voltage maybe from this 24 volt supply to maybe 240, and then the second transformer steps it up from 240 to say 2.4 kilovolts. I don't really know the voltage these arc welders or MIG welders run on, and that's how it's working. If that's the case, and this is driving the transformer, then this would be controlled by pulse width modulation. That's just a gut feeling for it. Let's see if we can prove this one way or another. So the first thing I noticed, and it's obvious, there's a large diode here, and that is connected to the collector of this, okay? If the other end of that goes to the negative end of this bridge rectifier, and it looks like it goes that direction, I think this tells us something important. So this is the anode of the diode, and this goes, does it, to here? It certainly does go to there, right. So this is ground, yeah, this is the same as here, ground. I know some of you guys don't like circuits that look upside down, so we can say that is to there. And we have a diode, quite a big one, connecting from here with the cathode to there. That's the same as the negative end of this. When we put the diode in the circuit, even without that, I think it should be clear, or it should be becoming clear to you guys now if you're learning, that that is to stop back EMF, and this is because this transistor is switching something like a relay, a motor, or a transformer primary. So I think that can tell us what that transistor actually does. Guys, what do you think? Is Richie right on this one, or is he not right on this one? Okay, because that's what I see. So if this transistor drives something big and heavy, well, there's an inductor here, but that doesn't look big enough. That, you know, if that inductor is in this circuit, I would suspect that this is a PFC type circuit, which is strange because they normally use a MOSFET, and that's a booster, voltage booster. But if that was a voltage booster, you know what, guys, there'd be another capacitor on the output side of it. Well, there are some 50 volt capacitors down here. But I tell you now, something else. If it was the PFC circuit, it would have a diode in it, but it would be the other way around. A PFC would go something like this. From your bridge, okay? Mains, generally, these things may or may not have a capacitor here. It doesn't matter to the operation of the circuit. Would have a MOSFET here. Okay. I've missed something out. Would have a coil here, which could be that big inductor we've seen. Something, it would look something like that for sure. And then this end would go to capacitors. This would be your PWM, and the diode in the circuit would be in that direction. and ours is the wrong way around. So it's not a PWM or booster. That makes me think this is just a filter and probably attached in with this capacitor somewhere. Where the legs go. Legs go here. Okay. That's connected to something that comes out here, orange. This is connected to the wire feeder. At one end of it does. And the other end, goes to our transistor on the collector. Oh. So I think we can say now that this actually doesn't do that, but we can say what it does do. And we'll draw it again. You see how this evolves, by the way? I mean, I know a lot of you guys watch me fairly regularly now. This is kind of the way I work. Usually just being quiet because I'm by myself, but I've got so used to you guys being here now. I just keep talking. Okay, something like this, capacitor. Okay, and then the transistor. Okay, something controlling this. Yeah, and then an inductor. Wire feed. Okay, and the diode is connected. We will assume that the other end of the wire feed goes to ground. Where else would it go to? And the diode is connected basically from ground. So I'll put that there. The diode is connected from ground to there to stop back EMF. This is the same thing as switching on the relay or anything else. Yeah, that's how that works. This will also help to stop spikes coming back in here as well, by the way, filtering for noise from the motor. Okay, so we can say we know with good amount of certainty now what this is doing. The fact the wire feed doesn't work and the output doesn't work makes me suspect there's something fundamental wrong, like power getting to these various chips. So I think what we'll do now is we'll actually power this up and have a look to see if we have a supply on here, if we have a supply on here. I wouldn't be surprised if this isn't oscillating, because this is probably triggered by something that will not happen because this isn't connected. So we can have a go around and see if we have like sensible voltages and signals here. Maybe some sort of enable that isn't there because something isn't triggering it. I hope we don't quite get to that because it could be a bit tricky to find out what without the rest of the equipment. But you know, guys, you can only really work with what you've got in front of you, yeah? I've just attached a couple of wires. So this is the negative of the bridge rectifier. This is the positive. This is where he connected his capacitor back across. Okay, capacitor's the right way round. Good. I've attached a negative of my meter here. This is the positive supply. So we'll put the power supply on. You can see we have set to 24 volts. What does it do? Does it draw any current? Well, it draws about 50 milliamps. The red LED is illuminated. Yeah, it's glowing. See it? So that is on. There's power on the board. Let's have a look. So the LM324 power supply is here. Nothing. There's only 3 volts across that. One is the positive and one is the negative. Let's have a quick look on the data sheet. Yeah, here. So 11 is ground. So the one with 3 volts on is a supply. That seems a bit low. Minimum supply for these things. Oh, says it runs down to 3 volts. So possible, I guess. And then the other chip, again, the supply across pins 4 and 13 on this one, with a positive on 13. Let's see what we've got on there. So we know now that this is ground and it was reading 0. This could be 3 volts. It is possible to run on 3 volts. And then this one, it's here, positive. 23 volts, that's more like I expected on that one. And this should just read 0. Pretty much. A little bit of voltage on there. But for all intents and purposes it says 0. Thing's drawing 50 milliamps. What's happening with this transistor here? So this is your power coming in. Yeah, 24. That is switched off. But this should be triggered with some sort of trigger or switch on here that we know about. Possibly grounding the pin with 3.3 on it, okay, to trigger that. So we seem to have a supply voltage at least. Anything on here? So that's 4.2. Is there any sort of AC on here? This is what you'd expect to be driving the transformer, but it's a very low voltage. Let's have a look. Okay, if anything interesting is happening there, I'll move the camera a little bit closer so you can see it. Yeah, what we got. So this is where the output is. No, there's just a DC voltage on there, there's nothing else. Yeah, just a DC voltage there, nothing else, okay? So what's happening on the output of this chip? We have an oscillator output on pin 4, and then outputs A and B. Yeah, I think this thing can effectively drive 1 or 2 MOSFETs. So that's where we should be looking for signals, output AB. These look like they're just open collector things. There'll be some sort of pull-up on there. Yeah, so this can be driven in different ways. Oscillator, here this looks like there's a clock signal coming in, but there is an oscillator in here. We can have a look. So pin 4, do we see anything? And on the outputs 11 and 14, do we see anything? Yeah, let's check that. Yeah, it does say here oscillator output. Okay, so pin 4, pin 11, pin 14. What have we got? Pin 4 is here. Something's oscillating. Okay, something going on. It's not triggered, but something's happening. Pin 11. So 9, 10, pin 11. Pin 14. They seem to connect to a rail. I mean, the different configurations this chip has. I'm just noticing. Something is getting a bit warm on here. Oh. This resistor, he says, gets hot. Does indeed get hot. Let me just get the thermal camera. Let's see. So, well, it tells us that this resistor here, which is the one that Roger told us is about 70 degrees. Was it that high? No, it's not that high. It didn't feel that hot. And then there's another one here, which looks like, yeah, the second one down. Oh, I see which one that is. Okay, so there's 2 resistors there, getting quite warm. 49. Oh no, it is 70 something, yeah. That one, and then there's another one up here, I think, somewhere. Let's have a look. There. 41. Oh, I see where that is. Okay. So we have 2 resistors, 3 resistors, one getting hot and the other getting fairly warm. Now this one is quite a chunky resistor, so you'd expect it to be passing some current anyway. Let's have a look. So what voltage across this? Well, that's 21 volts almost. I'll come back to that in a minute. Other ones here. One of these. That one. The reading is minus, so the current's passing in the opposite direction, about 22 volts. Across it, yeah. But this is a higher value resistor, therefore there's less current. This is a, was it what? 820 ohm. And then the other one is here, it's one of these, I think it's this one. That's about 4 volts. This one, if that's reading about 22 volts and I connect my meter to the ground again and I measure from this end, this is about 3.04. Does that go to here? This one, I think it was this side. 3.04. The chip isn't warm. You know what I'm thinking, don't you guys? You know exactly what I'm thinking now. So, resistance range or continuity, powered off. Here to here. That resistor is powering this chip. Yeah, that is powering this chip, and this chip, although it's not getting hot, is probably faulty. I mean, why would an op amp draw so much current? Look, this is 820 ohms, okay? 820 ohms, you've got 22 volts across it. Quick bit of maths. How much current is flowing into that op amp? Most likely where it's going, so I don't see anything else getting warm. So Ohm's law, yeah, V I R, the triangle. We know V 22, yeah, and we know R divided by 820, about 26, 27 milliamps. That seems quite a bit for an op amp to me. So I'm pretty sure we've come to the conclusion on this one that we have a faulty op amp. I don't have any of these here, but I can get one Friday from the electronic component shop and we can come back and have a last look at this. But I'm confident enough that the fault on this is a faulty op amp, and that is probably involved in both parts of the circuit, which is why nothing's working at all. Well, I'm going to go home. It's the end of the day. A couple of days will change that. In the meantime, what do you think? What do you guys think? Did I diagnose that one? Would you check anything else, or would you just change that? Get to the comments below, let me know, and we can try any suggestions you make. And if they don't prove anything different, we'll go with my suspicion that that is a faulty chip. Okay? Hope you enjoyed that, and I look forward to seeing you all very soon on Learning Electronics Repair. Ciao for now, guys.